Hello friends, welcome to this first technical lecture on thermodynamics and kinetics. So before beginning and getting into the technical aspects, at least the introductory ones on thermodynamics and kinetics, I would like to just mention few things on rather a general aspect. One is concerning the way attendance for this course will be taken. So since we are following the flip mode of lectures, the attendance will be in the form of a Google Sheet. It will be circulated to you after each lecture. So this Google Sheet will comprise of questions that is pertinent to the lecture that was delivered on that day. So if after listening to this lecture, you will be able to answer that question, and once you have answered that question and submitted the form, that will be considered as your attendance. So what I mean by that is, along with the link for a given class, a Google form will be circulated, and this Google form will comprise of a question that has been dealt with in a given lecture. So after listening to the lecture, you will be required to answer this question in the Google form, and once you have submitted this Google form after answering the question, it will be treated as your attendance. And secondly, since we are dealing with thermodynamics and we will be using a lot of notations, I'll be trying to write something on this whiteboard using a digital writing pad. So it is like writing on a piece of glass. So it means that at times my handwriting not be as legible. So in most cases, when it is not legible and I'm able to understand it, that it is not that clear enough, I will try to rewrite it. If not, please make some effort in order to decipher what is being written in the board. And of course, I will always be available to clarify whatever questions you have pertaining to a given lecture, be it on what is being written on this whiteboard and what are the concepts that are being dealt with. So without any further delay, let us get into the technical aspect of this course, that is thermodynamics and kinetics. Now, let's start where everything should ideally start. What is the meaning of different words that we considered in this course? So let us begin by considering the word thermodynamics. So in order to do so, instead of rendering a more specific approach, let us start with a generic statement, or let us start with a generic setup. Let us begin by considering an object. So let this object be a spherical ball. So the reason we are starting with a spherical ball is because spherical ball is rather easy to move, it is easy to play around, so therefore I would like to start with a spherical ball. Of course, you can start with any object. Now, this object is of a specific condition. Now, this object is often associated with, or it is present in a specific condition. So we have an object that is present in a specific condition. Now, this condition can be rather static, meaning it is immobile, it is not moving anywhere. The ball that we are considered, the object that we are considered is not moving anywhere, it's just static. Or it can be moving. So with time, its position can change from place to place. Now, when you consider an object and you have a condition associated with it, if this condition is immobile, if it is static, then we need certain parameters to define this condition. So you have an object, it is present in a specific condition. We need to know certain parameter to define this condition, to describe this condition. So if I say this object is static, the spherical ball that we have considered is static, in order for me to describe what the static means, what the static condition means, then I should know the position of the object. So when I know the position of the object, I can say, so with respect to time, if the position stays the same, then my object is static or it is immobile. So I consider an object and I state that it is in a specific condition, and in order to describe a condition, I need a specific variable, and that variable is the position. I need a specific parameter, and that parameter is its position. With respect to this parameter, then I define or I describe this condition. So when I say with time, when this position does not change, then the object that I have considered is in the static position or in the static condition. Now, with the same variable or with the same parameter, I can also describe the other condition, that is the moving condition. that is the mobile condition. So how can we do that is when we can just contradict, or we can present a description that is in contradiction to static. So in case of static, we define the condition as we have an object in a specific position and that position does not change. So that describes our static position. In case of a moving condition, when with respect to time our position changes, then our object is no longer in the static position, it is in a mobile condition, it is in a moving condition. So in order to describe a given condition of an object, we need a variable, and based on that variable we will be able to at least describe to certain degree of accuracy the condition of the object. We start with a condition, we associate, or rather we start with an object, we associate it to a specific condition, and in order to define this condition we introduce a variable. So we introduce position to define or describe the static immobile condition of the object. By describing a contradiction of the static condition, we were able to arrive at another condition, that is the moving condition. Now when your object is moving, even though the position alone gives you some sort of a description, it differentiates static position from the moving position. In order to be more accurate, in order to predict what will happen to this object at a given instant, we need to have additional variable as well. So these variables, they include velocity. If the condition associated with the object is such that it is moving at a constant speed, or if it is moving at a varying speed, then we need to know the acceleration. So in order to understand the condition that is associated with the object, we need certain variables. In order to describe a condition that is associated with the object, we need certain variables, and depending on the condition, the variables we use vary. So when your object is in the static condition, when it is in the immobile condition, the only variable that we need is position. We can say if the position does not change with time, then our object is static. If the object is moving, if the condition is different from static, then we need to know the additional variables, and using these variables we will be able to describe this condition that is different from static. Now when you want to be precise, we want to have a comprehensive description of this condition in which the object is present. So in that case we need to have some knowledge about, we need to have some understanding of the different or additional variables like velocity and acceleration. Now when you have an ideal system wherein you have an object that is in a given condition, and you want to play around with this object, what we mean by play around is we want to change the condition that exists in, and we want to see if we are able to predict it, if we are able to ascertain where this object would be in a given point of time. So all these things can be done by understanding the Newton's law of motion. So these things would have been introduced in your school days. So what essentially Newton's law of motion does is, it helps us understand, it helps us predict the different conditions, or helps us understand the position or the nature of an object, the way the object presents itself in a given condition, provided we know the different variables. So this Newton's law of motion, it was a breakthrough, for it helped us understand the condition of an object, be it static, be it mobile. It helps us understand or theoretically present the condition of the object. It helps us predict what this condition will be at a given point of time. Now, even though this Newton's law of motion, it was a wonderful breakthrough, we were able to build based on these fundamental laws that governed these condition of an object, that is static or mobile condition of the object, and the different variables that are associated with it. And based on these, even though we were able to discover many things, we were able to understand many things. For example, we were able to understand or postulate the planetary motions. So even though we were able to understand these many things, or it was quite expensive at applications where one concept or one other theoretical aspect was not largely associated with this Newton's laws of motion. So Newton's laws of motion, they dealt with an object in a specific condition. It dealt with how we can describe this condition. It dealt with how we can, in a given condition, how we can play around with the object and still predict where this object will be at a given point of time. it introduced different variables and how these different variables relate to themselves when we are attempting to study an object in a specific condition. And using this, we were able to expand these laws. So Newton discovered that, or we saw that, we understand that there is a specific law that relates these different variables. Despite all this, and despite its application, there was one concept that was not initially related to that of this Newton's law of motion. So we were able to impose force on a given object. The term force was introduced, was associated with this Newton's laws of motion. We were able to change a given condition of an object by imposing a force. We were able to relate these force to these different variables that we have considered. Of course, there are some variables that describe the object, for instance, mass. So by working around this, or by studying this behavior of this object under different conditions, we were able to relate these different variables, and we were able to postulate certain laws on how these different variables, they relate to one another and they follow a given specific, or they follow a specific relation. So all these things we were able to do. However, despite all this, so in addition to all these variables, we were able to also introduce force when we consider the condition of an object, be it static or mobile. So when we want to understand this comprehensively, just a ball rolling around, so when we want to understand that comprehensively, we were able to introduce these different variables and a set of laws that relate these variables in a specific manner. And it had huge applications, like to reinstate, we were able to understand or describe the planetary motions based on our understanding of this law. Now, despite all this, one theoretical aspect was not, or one theoretical concept was not directly associated with these object and its different condition, and that theoretical concept was energy. So even though now we understand that there is an energy involved, and this energy is nothing but the ability to do work and all those things, now we are able to understand. So now we say that we use energy to move this object. So these things, we were able to understand it now, but initially this energy, the concept of energy was not directly introduced in the framework of this Newton's law of motion. In the Newtonian mechanics, initially it was not introduced. So all these things, the movement of the object, the condition of the object, of course when it is static, and these things were separately dealt, and the concept of energy, it was separately dealt with. When we want to study an object where an object in a specific condition, a force is being imposed into it, and how the specific condition changes with time in response to this force we imposed, we went for Newtonian mechanics. We considered Newton's law of motion. We did not explicitly treat energy in this framework. However, what happened was, in the mid 18th century and early to mid, or in the end of 18th century and early to mid 19th century, so these are just date, in the end of 18th century and early to mid 19th century, it was realized that the work that we do can be, or the work that we do often produce some sort of an energy. It's produced a form of an energy which we now refer to as heat energy. So initially, whatever description or whatever variables that dealt with the object and its condition were often studied in the framework of Newton's law of motion. So like we saw, that these variables included position, velocity, acceleration, force, and mass. Now, the concept of energy was not directly associated with the Newton's laws of motion. So the energy was studied separately. However, in the 18th and the 19th century, end of 18th century and in the 19th century, it was realized that the work often generated a form of energy. So work can be transferred into an energy. So the reason this was a breakthrough, because the work often is described as the combination of force and distance. So if you want to have an expression, or if you want to quantify a work, you describe it as a combination or a product of force and distance. So force is something that is associated with Newton's law of motion. So yes, we saw here. And distance is nothing but the change in the position, another variable that is associated with the Newton's law of motion. So what happened in the early end of 18th century and early 19th century was two different domains. One domain that deals with the movement of an object under different conditions or under or various condition exhibited by an object under different force or under different surroundings. And there was another domain that dealt largely or exclusively with energy. In this period, it was realized that there is some sort of a link between these two domains. This link was established through the work, which is nothing but the product of force and distance, and the force and distance, they largely belong to the realm of Newton's law. And this work, it released or it rendered some amount of energy, so which belongs to a separate domain. So what we mean by that is, we have Newton's laws of motion, so Newtonian mechanics at one end, wherein we dealt with work. So this work, it depended on force, distance. This distance is again a factor that is governed by velocity, acceleration, and of course position. So we have the Newtonian mechanics, a separate realm of its own, the Newton's laws of motion, and this largely dealt with these aspects, and the combination of these aspects rendered your work. And it was realized that a specific amount of, when you work on a specific problem, a specific amount of work was transferred, or it was translated into an energy. So energy was released by doing some amount of work. And this introduced an interconnection between the Newtonian mechanics or the Newton's framework of understanding the condition of an object to the separate realm where energy was dealt with. Incidentally, this relation that the work released some form of energy was discovered while people were trying to understand what heat was. I don't know, you might have studied about this. So when people wanted to describe what heat was, they usually observed this form of energy while certain work was being done. Particularly while drilling the surface of the earth, they found that certain amount of energy was released, some form of an energy was released, and this is what they refer to as heat. So essentially, it was discovered in these early stages that the work can release a form of energy. The work that is usually associated with the Newton's law or the Newtonian mechanics, now it released a form of energy. And this, not any form of energy, in this particular case it was heat energy. And of course, eventually they discovered that work can also render several forms of energy, but initially this work can give you heat energy. This was the initial discovery that related these two different domains. And subsequent studies also proved that the energy can be used to do some work. Particularly, again here, the heat energy can be used to do or introduce some work. So it can be, heat energy can be facilitated to induce a specific work. So what we have is, we have a combination, or we have an interplay of two different domains. We have a link between two different domains now. So we initially had the Newton's domain, which did not consider energy, but now while one was working on how to understand the concept of energy, we saw that work produces energy, and subsequent investigation also allowed us to understand that it is possible for us to convert the energy into work, specifically the heat energy into work. So it means these are not two different fields, rather, so these can be coupled and studied in a single framework. So these two different fields, this was initially distinct. So this field of Newton, it was distinct, and this field of energy, it was distinct. Now we have a single, so it was this relation that the work produces energy enabled us to understand that both these can be studied in a single framework. And this single framework, wherein we study the combined effect of both heat and work, the interplay of heat and work, how one can be transferred to another, the work and heat, how one can be transferred to another, is what we refer to as the thermodynamics. So I don't know, you might already be familiar with what these terms mean. So thermo is nothing but heat, and dynamics is movement. And this movement is nothing, it's largely associated with the work we do, because we saw the expression for work, it has to do with the movement of a given object. So essentially what thermodynamics does is, it considers the interplay of the energy and the combined effect of how the energy and work, they play with each other, or how they combine with each other, how one can be translated to other. So what is the balance we can achieve out of it? So how one can be made to do another. How can one be translated to another? So that is essentially what thermodynamics deals with, and all the laws of thermodynamics help us understand, like how the Newton's law helped us understand or relate the different variables that describe a condition of the object. In the same way, the different laws of thermodynamics helps us understand how the energy and work they interplay, how they play with each other, how they mingle with each other, how in what way one changes to another. So essentially what thermodynamics deals with, or what thermodynamics is all about, is it treats work as a form of energy, or it's a transfer of energy, or an energy transfer. Like heat energy can be transferred into several other forms of energy. This several other forms of energy, one form of energy is the work. So heat energy can be transferred into several forms of energy, and one form of energy is work. And that essentially means that work is one way of translating the energy into. So that is what we will be dealing in thermodynamics largely. So in thermodynamics, we treat the work as a way of expending the energy. So a form of work is, in the framework of thermodynamics, nothing but a form of energy transfer. So any form of energy can be transferred into work, any form of energy can be transformed into the other form of energy. So when you are able to transfer a given form of energy into work, it means that work is nothing but a form of energy transfer. And that is what the framework of thermodynamics is all about. And this transfer of energy and this behavior of energy between the heat and the work, the heat and the movement, is what the very word thermodynamics means, and that is what we will be dealing in this particular course. Now, so we began with a simplistic consideration, a very general consideration. We began with an object. We associated a condition to that object. We needed certain parameters or variables to define this condition. And once we have defined this condition, we saw that in the earlier days there was one particular concept that was not associated with this discussion, wherein the different conditions were related to one another. And we saw that this particular or this theoretical concept, that is energy, was soon related to one another, and this relation, that is treating work as nothing but the form of an energy transfer, led us to the thermodynamics, where we are essentially combining energy to work. We are essentially treating work as an energy transfer, and in thermodynamics we are not considering any other form of energy. It is specific to heat energy. So based on this simplistic, or rather a very straightforward analogy, a rather straightforward starting point, we will try to understand some of the terminologies that we use in dealing with the concept of thermodynamics and dealing with our course on thermodynamics. So we began by considering an object. So this object in our case was a spherical ball. So in case of thermodynamics, since there is energy transfer being involved, instead of considering a spherical ball, we usually consider a section that is of interest to us, a section of this wide universe that is of interest to us. Now, when we considered a spherical ball, we were largely associated with, or we were largely dealing with its movement, its condition, and its condition was based on its position and its and largely based on its position and its acceleration and velocity and other features. We did not consider what is happening within the ball. However, in case of thermodynamics, we are considering the concepts like energy that is not on the surface of the ball alone. For that, we need to have an even specific consideration than the one that we rendered for the initial Newtonian concepts, the initial laws of Newton. So whatever understanding, so whatever consideration we rendered for this wall, it needs to be even more refined when we want to talk about the concept of energy. So therefore, this object that we considered in the Newton's law of motion, it takes a different form in the framework of thermodynamics. And here the analogy, the analogous term for the object in the Newton's law of motion, the analogous term in the thermodynamic framework is system. So what we considered, the object that was of interest in the previous framework, that is in the framework of Newton's laws of motion, in case of thermodynamics, that we refer to as system. And in case of Newton's law, the consideration we rendered to this object was quite straightforward. We were not interested in what is happening within the object. But here, since we are in thermodynamics, we are considering certain theoretical concepts like energy that needs some information about what this object is, then we need to have a refined definition for this system, and this object, which in the framework is called as system. So essentially, what we refer to as object in the Newton's framework is the same. It's the area of interest to us, it's the object of interest to us. That is what we refer to as system in the thermodynamics. It is the same, analogous. So you have object in the initial framework and you have system in the new framework of thermodynamics. However, the difference is we are not specifically interested in what is happening within the object in case of Newton's laws of motion, but we have to have an even more defined description of the system, which we will be eventually getting into. So just to express or just to introduce an analogy, we have object in the Newton's case and we have system in case of the thermodynamics. Now secondly, when you have a system, we need to have a surrounding that is different from or that distinguishes your system. So when you had an object, that was a specific area or that was a specific region of your interest. And this object had its own environment, so we were able to define this object based on its environment. So when we considered a ball, a spherical ball, we know what its shape was and how it appeared. So that helped us distinguish the object from its surrounding. And in the same way, when we want to consider a specific system, a system which allows us to study the aspect of energy and also the work cumulatively, then this system, it needs to be distinguished from what surrounds us. So we need to distinguish this system from the surrounding. So this system and the surrounding are separated by a layer which is referred to as the boundaries. So in case of, again going back to our previous analogy, in case of Newton's law of motion, we have a solid spherical ball. So there we are not interested in energy, or we are not interested in what happens or what form of transfer happens between this spherical object and whatever matter it surrounds. So we are not interested in that. However, since in case of thermodynamic, our primary interest is the energy transfer, particularly heat energy transfer, then we need to make a distinction between a system and the surrounding, and our boundaries should also be defined in such a way that these transfers are possible. Of course, not in all instances, but these boundaries should, in general sense, be defined in such a manner that these transfers, both the work transfer and also the heat energy transfer, is possible. So that is allowed by this boundary that separates system and the surroundings. So system is nothing but the object that we consider in the Newton's form or the Newton's laws of motion. However, given the specific nature of thermodynamics, this system needs to be separated from the surroundings in order for us to quantify the movement of heat and the movement of work. So therefore, we introduce a boundary to separate the system of our interest from the surroundings. And depending on the boundaries, depending on what this boundary allows, there are different forms of system that you could define. Now this we will, of course, there are at the very outset in many books on thermodynamics, they usually define what the different systems are, how we can define different systems based on what the boundary allows or what the boundary prevents from getting out of the system. So based on that, several different systems have been defined. However, I will not be doing that here, because when it is relevant, we will be introducing or we will be defining that system. So as of now, what we want to know or what is important for us is similar to the object. We have a system here. In the system, in case of thermodynamics, the system involves, or it is largely, it has to have some transfer of energy and heat, and even in some cases, you should prevent this transfer of heat and work. We need to have a boundary that separates it from surroundings. So it is not just any solid object. It is a system that we define based on our condition, so based on our boundary. So in order to make this distinction between system and surrounding, we introduce this boundary. Now, again going back to our previous analogy, we saw that in order to describe the overall, say for instance, the object that we were considering, in order to do that, we introduced the term condition. In order to discuss about what is happening to this object that we have considered, we introduced the term condition. We described what this particular object is doing what is happening to this particular object based on this condition. So we said this condition, or we saw that this condition can be static. It means this condition is associated with this object, and this largely reflects what is happening to that object. So let me repeat. When we consider the previous setup or the previous framework of Newton's laws, we introduced an object, and we associated a specific condition to it in order to describe what is happening to that object. So only when you define a condition, only when you associate a condition to the object, you will be able to say what is happening to it, or else all we just have is just a system. And only you have a condition associated with it, then we will be able to understand how this condition changes when you change the variables that are associated with it. So just having an object alone will not give us much of an information. We need to have every object that is associated with a condition, and we need to have some information about this condition in order to study this object further. The term that is analogous to conditions in the framework of thermodynamics is the state of the system. So like condition in the Newton's laws of motion, what we have in thermodynamics is the state of the system. So we saw the initial setup for us to understand the Newton's laws of motion was an object and a condition associated with it. And similarly, when we want to understand the thermodynamics, we need to have a system that is separated from a surrounding through a boundary and a given state that is associated with the system. So you have a system that is analogous to object in the Newton's framework, and you have the condition that we refer to as state in the framework of thermodynamics. So the combination of system and state helps us describe what is the condition of a given object in the thermodynamic setup. So it is the combination of system and state. So we can have just a system. We can say, okay, this is a system, but in order to describe what is happening in that system, we need to know its state. If the system is doing something, or if it is static like we saw, if the system is moving like we saw in the Newton's framework, if the system is doing something or it is moving, if the system is static, in order to say that, we need to know the state of the system. Now again, moving back to our previous analogy, we saw that in order to describe the condition in the Newton's framework again, in order to describe the conditions of an object in the Newton framework, we require certain variables. So we required the position, if the object is moving, the velocity, of course, and if the object is moving at a varying velocity, then acceleration. Now, in order to describe the condition of a given object, we needed certain variables. In the same way, since we have now defined, or we have now described based our system and the state based on this analogy. So basically what we have done is we have defined our system and state based on the rather straightforward starting point of the Newton's law, the straightforward starting point of an object under its condition. We have defined our system and state. So we saw that since this condition it requires certain variables to describe it, we need also certain variables to describe the state of the system in the thermodynamic framework. In the Newton framework, you have a condition, you have variables defining it. In case of thermodynamic framework, you refer to the condition as state, and you need certain variables to define the state of the system. Now, there are two ways to define the state of the system when you are considering the thermodynamic framework. So the one way can be referred to as bottom-up approach. Bottom-up approach. So what bottom-up approach means is that we consider the different entities, the fundamental entities that constitute your system. We break down the entire system into smaller pieces. Often these pieces are atoms or molecules, these fundamental entities, and then we study the behavior of this fundamental entities. We study how these fundamental entities behave within the system, and then sum it up in order to describe the overall state of the system. So when we essentially want to describe a state of the system, So there are one way of doing it is we break down the entire system into smaller pieces and we study the individual pieces, how it's behaving, and then combining all the understanding of the behavior of all these individual pieces, we describe the state of the system. So this is a bottom-up approach, and the state of this individual fragments or the individual entities, we refer to them as microscopic state because we are breaking down the entire system into smaller pieces. So the state that is associated, the condition that is associated with each of this state, which is again, it is not visible to us, we have broken it down into smaller pieces. Therefore, since we have reduced the size of the system and now we are considering the individual subsystem or the individual entities associated with the system and the state of these individual entities, we refer to this state of this individual entities as the microscopic state. And by combining or from the cumulative understanding of all these individual microscopic states, we then will be able to describe the overall state of the system. So this is what we refer to as the bottom-up approach. Now the problem with this bottom-up approach is that the entities are not few in number. So usually when you want to have a system that is perceivable by us, that we can see, then at least it should have something around 10 to the power 23 entities. So if you are talking in a generalized term, again this is a generalized approach or generalized perspective. So if you are talking in a generalized term, in order to study the state of the individual entities and then related to the overall system, you need to know the behavior of close to 10 to the power 23 entities. Again, you need to know how these 10 to the power 23 entities behave. Now, in order to know the behavior of each of these individual entities, you need to then introduce different parameters. So let me repeat, when you break down your system into smaller fragments, you break it down into 10 to the power 23 entities that you can handle. And this system, when you say we can handle or we can study, in order to study that, you need to know the different behavior exhibited by these 10 to the power 23 entities. And in order to study this behavior, we need to introduce certain variables. So it is interesting to know why we reduce it to 10 to the power 23. You might have already understood it, because when we are reducing it to atoms, we consider when we treat individual entities as atoms, or when we treat atoms as this individual entities, here still the Newton's law, it prevails. Still the Newton's law works in when you treat the individual atoms as the entities. So that means you will be able to predict the behavior of individual entities based on the Newton's law, and then you can combine all these and then express the thermodynamic state of the system. So that's the reason why we have this magic number 10 to the power 23. So when you have a macroscopic, or when you have a system that you can perceive, when you want to have a system that you can study, that system generally it needs 10 to the power 23 entities or atom. The reason we restrict ourselves to atom is because the subatomic range, the Newtonian mechanics does not work. So the maximum length scale wherein the Newtonian mechanics works is the scale of the atoms, and that's the reason we stick with or treat the atoms as the entities. And using the Newtonian mechanics, you will be able to understand the behavior of each of these atoms, and combining all these behaviors, you will be able to then ultimately describe the state of the system. So that is one way of going about. Again, this would involve Newton's laws of motion and the variables associated with it. So even though you will be dealing with 10 to the power of 23 atoms, you need to include all the different variables that are associated with each of these atoms. So and let it be the different variables that are associated with each of these atoms. So you need to know these many, or you need to have an understanding of these many behavior of these many atoms involving these many variables. Only then you will be able to understand the state of the system when you take the bottom-up approach. However, there is another approach which is top-down. Now, in case of top-down, what happens is that instead of breaking down the system into smaller pieces, into its elemental, or rather into its fundamental state, wherein the Newtonian mechanics can be introduced to understand its behavior and then track back to the entire state of the system, we can consider the entire system that is perceivable to us, that is the entire system that we can see through our naked eyes. This system we can treat it as it is. So we can treat it in the macroscopic scale. So as opposed to microscopic, breaking down and looking into the individual particles, individual entities, we can consider the system in its macroscopic scale, the scale that is perceivable to us. And in this scale, we can define, or we can fix certain variables, or we can define the state of the system using specific variables. And these variables help us to describe the state of the system, and these variables are different from what we consider, or what we would have considered had we taken the bottom-up approach. So essentially, given that bottom-up approach requires a lot of information, we go for top-down approach. In case of top-down approach, first of all, our perspective changes. We will not be breaking down our system into smaller entities and studying each entity individually. We will be considering the system in the macroscopic scale, the system as we see it, and we will be describing the state not based on the variables that are associated with Newton's law and that will be associated with the small entities or individual atoms. We will not be doing that. We will be introducing our own variables to understand the state of the system, to define the state of the system. So in thermodynamics, what we will not be doing is we will not be studying the state of the system. We will not be describing the state of the system based on the behavior of the individual entities, but rather based on the macroscopic scale that we see our system in. So we will be using, or will be employing a definite variables, the macroscopic variables, to describe the state of the system. So the reason we are able to use a different set of variables to describe the state of the system in the macroscopic scale is because when you fix certain variables, the state of the system is fixed, both microscopically and also macroscopically. So let me repeat, it is possible for us to consider the system in a macroscopic scale and fix the variable and define the state using certain variable is primarily because when you fix certain variable, the state of the system is fixed, both the microscopic state and also the macroscopic state. So that is the reason why it is possible for us to select certain variables and then define the state of the system based on it. We need not know the 10 to the power 23 terms in order to define the state of the variables. Now, by selecting specific variables, by identifying specific variables, we are able to fix the state of the system, and using these variables alone, we will be able to describe the state of the system. And these variables that allow us to describe the state of the system is what we refer to as the thermodynamic variables. Just to pull it all through, we saw that the condition that is usually associated with the object in the Newton's laws of motion is nothing but the state in the thermodynamic framework. Now, in order to describe the state, we can take the bottom-up approach, wherein you consider the Newtonian behavior of individual entities, sum it all up, and describe the state. And because there are too many entities, it becomes too difficult for us. In addition to the entities, you need to consider the associated variables, so it becomes too difficult for us. Then we go for identifying variables that can help us define the state of the system in a macroscopic scale, not as individual entities, but the system as a whole. The scale that we perceive, the scale that we operate on, the scale that we see. Now, the reason we are able to the reason I'm reiterating it because we need to know why we are able to identify such variables. The reason we are able to identify such variables is because when you fix these variables, you fix the state of the system, and when the state of the system is fixed, then essentially you will be able to describe the state of the system based on this variable. So again, when we say the state of the system is fixed, it's not fixed in the macroscopic scale alone. So whatever individual variable that each of these entities are associated with is also fixed when you fix the thermodynamic variables. So these thermodynamic variables, the bottom line is, help us understand or describe the state of the system. To view it another way, these thermodynamic variables help us fix the state of the system. Now, again, going back to the previous analogy, so we began with an analogy and we will be trying to relate each of these thermodynamic terms based on that analogy. So going back to analogy, we saw that depending on the state of the or condition of the object that we considered, we needed different variables. So when the object is static, we wanted to know its position in order to describe this condition. When it is moving, we wanted to know its velocity if the object is moving at a constant speed. If the object is moving at a varying speed, we need to know its acceleration. So we need to know these variables in order to understand the condition of the object. Now let us try to use that concept or understanding in the thermodynamic framework. Now it is important for us to, or you can rather understand, or it is quite, if you think about it, it will come to you that velocity and position are rather related. Meaning, by studying how this position changes with time, you will be able to predict the velocity. And same goes with acceleration. Meaning, by understanding how the velocity changes with time, you will be able to quantify acceleration. So, depending on position, you will be able to quantify velocity. So, depending on velocity, you will be able to quantify acceleration. So, position is the one fundamental variable that dictates the other two variables. So, when you know the position of a given object, then you will be able to define its velocity and acceleration. When you know the position of the object for a given time, so again, the time is another variable that we need to consider. So, when you know the position of the object at a given time, then you will be able to predict its velocity and also its acceleration. When your object is static, then the time, the influence of time is 0. It is a time independent condition. So all you need to know is position. But when your object is mobile, then you need to know, all you need to know about is the position, that is this variable here, and the time. When you know these two variables, then you will be able to calculate the velocity and acceleration. So essentially what we mean by that is, or what we can understand is that these, even though it might appear that we need so many variables to describe the condition of a given object, it all boils down to two variables, that is position and time. Even though your object might be moving, or it might be behaving rather erratically, exhibiting different velocity at different points, if you are able to understand its position and time, you will be able to then estimate its velocity and acceleration. So what essentially it boils down is that in order to define a condition, you need not have to know all the individual variables, you just need to know the independent variables. So the variables that we use to define a given condition of an object in the framework of Newton's law can be distinguished into independent and dependent variable, and this dependent variables can be calculated from the independent variable. So this helps us just to ascertain position and time. So when we are able to ascertain or determine position and time for a given object, then we will be able to estimate all these different other dependent variables. So the same goes for thermodynamics. So here we now identified that a system can be fixed, a state of the system can be described by a specific set of variables called thermodynamic variables, and by fixing these variables you will be able to fix the, or by setting specific values to this variable you will be able to fix the state of the system. Now it is possible to distinguish these variables into two. One is the dependent variable, the other is the independent variable, like the ones we did in case of the Newton's laws of motion. So essentially, when we want to fix the state of the system, we need not determine the different variables, we just have to focus the independent variables, because from the independent variables you will be able to calculate the dependent variables. Now when we want to describe the state of the system, it is possible for us to just identify, calculate the independent variable, and then calculate the dependent variable, and then express the overall state of the system. So similar to the Newton's laws of motion, wherein the condition was described with several variables, and in these variables there was combination of dependent and independent variables. In thermodynamics as well, we have the combination of dependent and independent variables to describe the state of the system. In order to fix the state of the system, we just have to set a definite values to the independent variables. By setting a definite value to the independent variable, we are ultimately fixing the dependent variables as well, thereby fixing the entire state of the system. So with this, I would like to wind this lecture up. We will try to build on this understanding in the subsequent lecture. So we will try to make it, we will try to move away from this analogy to the specific concepts in the subsequent lectures. Goodbye.